Alright, in this crash course we are going to look at the things you need to know related to bonding for the AP exam, how to draw structural formulas, looking at electron and molecular geometries, hybrid orbitals, and then closing with what we look for in resonance, formal charges, and the different bond energies. As an example, let's consider the formula of the azide ion. That is the N3 negative ion. So let's talk about as much as we can related to this simple little formula. So how do we draw a structural formula? The first thing we need to know is our valence electrons. Well, the valence electrons is based on the periodic table. Nitrogen is in group 15, so that means it has 5 electrons each times 3. That's actually 15 electrons, but then plus 1 more for that negative charge. So I have 16 valence electrons, and I have to use them all to build a structure. With only 3 atoms, I'm going to just guess that they are in a row. In fact, that is correct. The AP would probably give you a template like that, and you have to fill it in. And then if I start with just single bonds and guess that I fill in the octet everywhere, remember the octet means every atom wants to feel like it has 8. The nitrogens on the right and left would need 6 more electrons. The central one would need 4, but if I do a count, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, this structure makes me need 20. I don't have 20. I only have 16, so I have to use only 16. I'm off by 4, so I need to get rid of 4, but then still share. And I'm going to share 1 pair where I used to have 2 pairs. And I'm going to do the same thing to the other nitrogen as well and share a second pair. Now what I've done is I've still kept the octet around every single nitrogen atom. If you count, they all feel like they have 8, but my total is 2, 4, 6, 8, 10, 12, 14, 16, and that's the correct structure. You might see the bracket notation where you put charges around it. It would be a negative charge in this case, and that's a valid structure for that particular molecule. So that takes care of structural formulas. Now, in terms of geometries, geometries can be electron or molecular. There are 5 electron geometries to consider. The electron geometries have to do with how many domains you have. They are in name linear, trig, planar, tetrahedral, trigonal, bipyramidal, and octahedral. Now, for the purposes of the AP, you're not going to see trig pyramidals and octahedrals. In all likelihood, it will be the other 3, a linear, a trig planar, or a tetrahedral one. The molecular geometries are a bit more involved. They describe the shape of the molecule, and sometimes they're the same as the electron geometry. For example, this one. This has 1 central atom with 2 peripheral atoms that experience repulsion between the shared electrons. So it doesn't adopt a bent shape with 2 nitrogens like that. That just doesn't make sense. It stays in a straight line. So we call it like we see it. This is a linear molecule. And we will see other examples when we look at some practice problems in a moment. But that's a quick rundown of geometries. Hybrid orbitals, really all you should know is they go hand in hand with certain geometries. There are 3 to know: SP, SP2, and SP3. And SP hybridization goes with a linear electron geometry, and SP2 goes with a trig planar electron geometry, and an SP3 goes with a tetrahedral electron geometry. And those furthermore go with bond angles. Shapes of molecules have bond angles, and a linear geometry has a 180-degree bond angle, whereas a trig planar has 120, and a tetrahedral is 109.5, roughly. It depends on the actual atoms attached, but that's a good rundown. And then lastly, what about resonance, formal charges, and the energy of these bonds? Well, let's redraw that azide molecule for a second. Here is the azide molecule, and it's overall got a negative charge, but the negative charge is not distributed. The negative charge actually can be drawn as if it's on specific atoms or a combination of charges. So for this, we need to teach what formal charge is. The formal charge is the valence electrons minus the bonds you see minus the dots that it has. That's valence bonds, and dots. It's a trick for tracking our charge separation in a molecule. So if I think about the nitrogen on the right, its valence would be 5, it's making 2 bonds, and I see 4 dots. So 5 minus 2 minus 4, this would have a -1 formal charge. I'd put a minus. The nitrogen over here would also have a negative formal charge for the same count. And then the nitrogen in the middle, well, it's a valence of 5 minus 4 bonds minus 0 dots. He actually has a +1 formal charge. So notice that the overall sum of the formal charges adds up to -1. You would never put both. You either put the brackets and the charge or the formal charges, but not both. The AP seems to lately prefer students understanding and using formal charges, so I would start to use them as you're practicing. What about resonance? Well, resonance is a way of drawing a different structure that's equally valid, or at least also valid, as the original one because it uses the same electron count. The Z ion can also be drawn like so, where you have one single bond and one triple bond as opposed to 2 doubles. This still satisfies the octet, and this still uses the electron count. Now if I look at the formal charges, you still have a plus on the central nitrogen and a 2 negative on the nitrogen on the left, so we still have a net of -1 overall, and it's difficult to say which of these resonance contributors is better. I would suspect the one on the left is preferred because it has smaller charge magnitudes, and it really shows how that's delocalized throughout the entire molecule. Frankly, there's one other resonance contributor that just swaps the triple and single bond, and that does count, where you would have still a positive on the central nitrogen, but now a 2- on the rightmost oxygen. We'll wrap up with just the energy of bonds, and that's when single, triple, and double bonds are not all the same energy, nor are they the same length. For this, you should be comfortable looking at a potential energy diagram. It's usually drawn with some kind of dashed line horizontal, and then there's going to be a dip and then a ending point along that axis. And what you need to know is that that trough is the lowest point. That's your bond energy in the vertical direction and your bond length in the horizontal direction. So that's your energy and that's your length. And what you should know is that multiple bonds, like so, are stronger than double bonds between the same 2 atoms. Stronger. But they are also shorter. So in terms of length, multiple bonds are shorter and stronger, and then the opposite is true for pi bonds. You can think about why that is. A sigma bond is just one single bond, but a double bond is a sigma and a pi, and a triple is a sigma and 2 pi bonds. So as you're adding more and more orbital overlap, you're getting a stronger bond, and the atoms are getting closer to each other as they get more and more overlap. So compared to this, let's say this was a triple bond, my double bond would be not as low and farther out, and my single bond would also be not as low and even farther out. So strongest, next strongest, weakest, as we go from triple to double to single, etc. Okay, let's look at some practice questions and see if we can make sense of all these topics. So first off, molecules exist in such a way that they maximize formal charges of 0. Based on this, which best represents H3NO? Well, let's go get the formal charge of every single atom in these structures. A singly bonded H is not going to have a formal charge. An oxygen, if I look at oxygen, that would be a valence of 6 minus 2 bonds minus 4 dots. That's 0. Nitrogen has a valence of 5 minus 3 bonds minus 2 dots. That's also 0. So there's no formal charges anywhere in this thing. We don't have any formal charges, so I don't need to draw anything except maybe I'll put 0 everywhere. All 0. Right next to it is not the case. If I count oxygen as 6 minus 1 minus 6, that is a negative formal charge on the oxygen. Nitrogen would be 5 minus 4 bonds minus 0 dots. That is a +1 formal charge. So not as good as A. because B has some formal charges. C would have formal charges. There'd be a plus on the oxygen, and there would be a minus on the nitrogen. And D has formal charges. D would have a +2 on the oxygen. That comes from 6 minus 4 minus 0. And the nitrogen would be a -2 formal charge. So that's our worst one. So A looks like the best because it's got no formal charges. Right below it, which molecule is polar? Polarity has to do with asymmetric distribution of charge. SNAP. If you are symmetric, you are non-polar. If you are asymmetric, then you are polar. Symmetric, non-polar. Asymmetric, polar. Symmetric means completely symmetric about the central atom, and don't be fooled by the way some things are drawn. That BF3 molecule right there, if you drew that out, that is a trig planar geometry, both electron and molecular. That would look something like that, and that is totally symmetric about the boron, so that is non-polar. Carbon dioxide is linear, also non-polar, because about the central atom, it is completely symmetric. The nitrogen is a linear non-polar molecule, totally symmetric. But B is polar. B has asymmetry because there are, even though it's a tetrahedron around the carbon atom, 2 of the bonded atoms are H's and 2 of them are chlorines, so there is an uneven distribution of electron density. You have dipoles pointing toward the chlorine atoms that are much more significant and in different directions than the little tiny dipoles that might be pointing toward the carbons. So B is the only one that's polar. Next, what's true of a binary compound? That means 2 elements with the same electronegativity. So I'm just going to make one up that would be like the bromine molecule. Same electronegativity, equal pulling, no polarity. The compound has properties similar to both elements. Not likely. I mean, there's if they have the same electronegativity but they're different elements, this might be bromine and just, I don't know, something else, who knows. The bonding is non-polar covalent. Yes, that is the best answer, because if they have the same electronegativity, there is no polarity of that bond. This does not predict boiling point. This does not predict ionic bonding. Ionic bonds is when they have very different electronegativities. Last multiple choice, which compares the strength of the carbon-carbon bonds in the structure below. Well, that double bond is a sigma and a pi. That single bond is just a sigma, so the double should be stronger. So the bond on the left is stronger because it is a double bond. That sure sounds right. Let's check the rest. The CC bonds are the same. No, that is incorrect. The CC bonds are the same strength. Nope, still not correct. The bond on the right is stronger. Nope, not right. It doesn't matter how many hydrogens you have. It's all about the fact that that extra pi bond makes it stronger. Let's wrap up with a short answer question. The graph below shows the potential energy of 2 nitrogen atoms separated by their distance. Indicate the distance that's corresponding to where we would see the nitrogen by just putting an X on the horizontal axis. So that lines up with how far down along the x-axis it is. So that's going to be right there. That's where it hits that distance. B, on the same graph, sketch the curve that would be expected for 2 oxygens. So if I consider a nitrogen molecule, that's a triple bond. But an oxygen molecule is only a double bond. And nitrogen should be shorter and stronger. Those go hand in hand. So compared to nitrogen, an oxygen would be longer, so it would be farther along the x-axis, and weaker, so not as deep. So I'll just sketch maybe where its x should be, its trough, and maybe it's right there. So relative to that, it would go not as deep and not as far out. That's what they're going to look for. Relative to that dip should be weaker and longer. Okay, that's a good rundown of the kinds of questions you might see on the AP relating to bonding. Thanks for watching.